In 1905, Einstein explained the photoelectric effect. Photoelectric effect, if you remember, says that when light of a certain frequency, let's say red, strikes a metal, an electron will sometimes be ejected. If that photon had sufficient frequency, therefore sufficient energy, an electron would be ejected. Arthur Compton noticed 3 years later in 1908 that when light of a really, really high frequency and therefore high energy, we're talking like X-ray photon, X-ray energy, when a high energy photon strikes a metal, then an electron will be ejected. But he noticed that a second photon, a less energetic photon, will also be ejected. So we're not talking about visible light here. I'm just representing it by visible light because you know the difference between frequencies of different colors. Let's say if blue light shone upon the surface and an electron is ejected, well, we also get a red photon ejected as well. Now, classical theory, which we usually define as pre-Einstein, pre-1905, classical theory would have predicted that this photon had to be the same. The initial photon would be the same as the second photon. Let me give you an analogy here. We have a car on the side of the road. We have a truck. Okay, we've used something similar to this before for something else. It's going to be a little bit different, though. The truck is traveling at a certain speed with a certain energy. It hits the car. The car is ejected. The car goes off into the ditch, right? The truck bounces off. The truck that bounced off is the same as the truck that hit it in the first place, right? Classical theory would predict that the photon that struck the surface was going to be the same as the photon that bounces off of the surface. But the observations contradicted that. The observations showed that the second photon was less energetic than the first photon. So let's go back to that analogy for a second. The truck, is it the same truck that bounces off? Yes, but the energy of that truck is different than the energy of that the truck was when it struck the first car, right? It's less. Because if the truck strikes the car takes away some of that energy. There's less energy available to the truck. Now, in the context of that example that I just gave you, that analogy, the truck looks the same. But in the context of EMR, lower energy, if the truck that strikes it is blue, the truck that bounces off is a lower energy, therefore a lower frequency, therefore a different color. So, classical theory would have just said, a truck's a truck. When a truck hits it, the truck bounces off, it's the same truck. But photon theory or quantum theory says that when the truck hits it, okay, that's great, the truck bounces off, but it's a different truck. It's a truck with a lower frequency or a lower energy. So this is another piece of evidence to support the particle theory or the photon theory of EMR. Refraction, diffraction, interference, polarization, wave theory, photoelectric effect, and Compton effect now we've got supporting the particle theory of EMR. How does Compton explain this? Well, he explains it first by saying that photons have energy. That's not new. Einstein said 3 years before that photons have energy equal to h times f. But he said now that photons also have momentum. That's the big takeaway from this. Photons have momentum. That's the original part of this. Photons have momentum. And this is really just a collision. Just like the truck colliding with the car, this is just a collision in which energy is conserved and in which momentum is conserved. If we analyze this using conservation of energy and conservation of momentum, then we nail this. But we got a problem. We have a problem here. The problem is that if we analyze this situation of a photon hitting an electron, and then the electron bouncing off and a photon bouncing off, it's difficult to analyze this using momentum when photons don't have any. What do you need to have momentum? Mass. Photons don't have mass. So, how do we reconcile this? Well, Compton said basically that photons have mass. Photons have momentum. but we've got to establish how they can have momentum when they don't have any mass. You guys remember the equation that we used for momentum the very first day of Physics 30? Better. What is it? Anna, what is it? Momentum. Oh, come on, you know this? What does it entail? E is equal to m times v. Very first day of Physics 30, right? P is equal to m times v. Right? We would use that still to find the momentum of a truck, the momentum of a baseball, the momentum of a proton. But photons, particles of light, don't have any mass, so it becomes difficult to use this equation. Now, it's Einstein, again, that comes into play here. Einstein said that energy and mass are two different forms of the same thing. Kind of like ice and water. Ice and liquid water, that is. Ice can be changed into liquid water, and liquid water can be changed into ice. But ice isn't water, and water isn't ice. Mass can be changed into energy, and energy can be changed into mass. Mass isn't energy, and energy isn't mass. But they're really two different forms of the same thing, just like ice and water are two different forms of the same thing. If you have a certain amount of ice, you don't have water, but it's like you have a certain amount of liquid water. If you have energy, you don't have mass, but it's like you have a certain amount of mass. Energy and mass are just two different forms of the same thing. Now, he gave us an equation that described the relationship between energy and mass, probably the most famous physics equation ever, maybe one of the least understood physics equations ever. Anybody want to take a guess at what it is? E equals mc squared. Einstein said that if you have a certain amount of mass, you don't have energy, but you do have an equivalent energy. It's like you have that much energy. It's like saying, okay, I get a certain amount of ice. I don't have liquid water, but it's like I have this amount of liquid water. What Compton did is rearranged Einstein's equation. Said, listen, I don't have any mass here in these photons, but I do have energy. Photons have energy. That was established. That was well established 3 years prior. So if I have energy, it's like I have mass. It's like I have this much mass. So here's what Compton does now. He takes this equation for equivalent mass, subs it back into here, and says P is equal to E over C squared times V. But what is V? What does V stand for here in the context of a photon? Speed. Speed of what? Speed of a photon. Speed of light. What's the speed of light? Speed of a photon. 3 times 10 to the 8. What's the symbol we often apply to that? C. So let's replace that with a C. P is equal to E over C squared times C. That means one of the C's cancels here. And we're left with P is equal to E over C. Now, on your data sheet, it doesn't actually say P is equal to E over C. Rather, on your data sheet, they take a different form there. It says E is equal to P times C. E stands for the photon energy. This is not new. We've already seen photon energy. E is equal to HF, hc over lambda. This one is new. This is photon momentum. And this, is, of course, is the speed of light, 3 times 10 to the 8 meters per second. What units do you think photon energy should be in? Make it joules here. Make it joules. Don't even go EVs here. Make it joules. Photon momentum. This is kind of weird, actually. It's weird to have a unit that's kilograms meters per second when you don't have mass. But that's the units for momentum. If you remember back to September, that's what we use for momentum. Now, in your data sheet, there's one more equation with momentum in it. Looks like this. All they've done with this one is replaced E with hc over lambda, canceled out C, and rearranged it to take this form. The good news is you don't have to derive these equations. You have to know the two equations that are boxed off there where they are on your data sheet, what they're used for. Okay, know that these ones on the right-hand side of this board are used for photon momentum. Know that this one is used for baseball momentum, proton momentum, momentum with mass, momentum without mass. I just derived them to show you where they came from, that they're not just made up. Now there's another equation as well, and this is where we'll finish off today. This one's an ugly looking one. Good news is it is on your data sheet. The good news is we don't have to derive it because it's really, really hard to derive. I can't derive it. I've tried and I couldn't derive it. But you do have to know where it comes from, that it does come from, at some point, the law of conservation of energy and the conservation of momentum. Here's what it says, delta lambda. What does that stand for? Change in wavelength, yeah. If a photon decreases in energy, and it does, right? The blue photon it struck the surface, an electron was ejected. A less energetic photon was ejected as well. A red photon was ejected. If the energy went down and the frequency went down, then the wavelength will go up. So this is the increase in wavelength. The wavelength of the photon will increase, and that's going to be measured in meters. H is Planck's constant, of course, and that's going to be 6.63. Don't use the 4.14 value here, ever. Always use joules. C stands for the speed of light, 3.00. And M stands for, no. No, this one's an easy one. M stands for, don't overanalyze it. Mass. Mass of what, though? No, not mass of photon, because photons don't have mass, right? No, it's not the equivalent mass. Okay, I see where you're going with that, actually, but no, it's not the equivalent mass of the photon. What other thing has mass? The electron. It's the mass of the electron. So it's 9.11 times 10 to the minus 31 kilograms. Now, theta is the scattering angle of the photon. That's going to be measured in degrees. If you look back to this diagram over here, right? The photon scatters at a certain angle. Whatever that scattering angle is theta.